Hi, in this video we will learn about limit at infinity, and we will learn that what is a horizontal asymptote and how we can compute horizontal asymptotes. Let me start with an intuitive definition of limit at plus infinity. So the limit of a function f as x approaches to infinity or plus infinity is equal to L, and the way we denote this thing is limit of x goes to plus infinity of f of x equals to L if the values of f can get as close as we want to L. So if the values of f can get arbitrarily close to L, well, provided that x is sufficiently large. So it means that from a point on to the right, the values of function gets as close as we want. So you want f be close to L less than half a unit. I will find the next from that point on function is the distance of function and L is less than half, and so on. Well, to be able to define about the values of function for large x's, we have to assume that let f be a function well defined. This needs to be defined on an interval as a plus infinity. If it is not defined at large numbers, you cannot talk about the value of the function and if it is getting closer or not. Well, in terms of the graphs of the function, limit is L if, so let me just draw these graphs, different possible cases. Let's say all these guys are y equal to L. L the value, L the limit. So the function can get closer to L, something like this from up. As you see, as x goes to plus infinity, function gets closer and closer to that. Or something like this. Or this is something that usually people ignore. It can intersect. It can intersect with that y equal to L infinity. But the point is that as we move to right, it gets closer and closer to the well, this is the definition of the function as x goes, the limit of function as x goes to plus infinity. One can have a similar definition for negative infinity. In that case, the function to start with needs to be defined on an interval negative infinity to a, and then we write it as limit of f of x as x goes to negative infinity is equal to L if the values of f can get arbitrarily close to L, provided that x is sufficiently large negative number. So this thing, basically the graphs of the function would look like something like, let me just draw some red ones. As x goes to plus negative infinity, this is negative infinity. This gets closer and closer, or something like this one. And you see similarly you can see what will happen there. Okay, so let's just start with some examples and study some of the functions limit using their graph. Use the graph of the given functions to find the limit limit at infinity. Their limits at infinity. What are the functions? The first one is the constant function, f of x is equal to 2, for example. Yes. Then the second one is f of x equals to 1 over x. And the third one, f of x is equal to e to the power x. And the fourth one is f of x is tan inverse of x. Let us just look at the graph of these functions. So, okay, so this function is constant y equal to 2. So its graph will look like this, yes? Well, if it is a constant 2, it cannot get even closer than anything to 2 itself. So it means that limit of f of x, I should have written that in black, as x goes to plus infinity or x goes to negative infinity, at both cases these are just constant number 2. It cannot get better than that. It is the closest possible thing. It's itself. Yes. How about this other one? F of x is equal to 1 over x. I hope you know the graph of this guy. This is simple function, rational function, and it goes like this. And you can see as x moves to positive infinity, these values get closer and closer to 0. So in other words, limit of f of x as x goes to plus infinity is 0. How about negative infinity? Well, we have to look at this side. As x goes to negative infinity, function has limit again 0. Okay. For e to the power x, let's see what we have for e to the power x. So you remember the graph of this function? It's something like that. So as x goes to negative infinity, limit of e to the power x as x goes to negative infinity, the function gets closer and closer to the x-axis, which is y equal to 0. And that means that the limit is 0. How about limit of f of x as x goes to plus infinity? Well, actually this blows up, gets big large numbers. So the limit at plus infinity does not exist. Or you can specifically say that, well, as we move to right, this guy grows large and large, big and big. So this is plus infinity. Yeah. How about tan inverse x? This is nice function. You have to know the graph of this function. So the graph, it is inverse of tan, yes. And when you sketch the graph, what you notice is that, okay, there is 2 numbers. pi over 2 and negative pi over 2. And the function goes like this. Okay. Almost. Yeah, here should be a little bit steeper than that, like this guy. Yes, it's better this way. And as you can see, when x goes to plus infinity, this function gets closer and closer to the line pi over 2, y equals to pi over 2. And as x goes to negative infinity, limit of tan inverse x, as x goes to negative infinity, the function gets closer and closer to negative pi over 2. So these at least that last three things, these functions are very important. You have to know the graph of these guys and be able to see what happens to the function as x approaches to plus infinity or minus infinity. Indeed, we have generalized versions of these guys. I will write that as fact, while your book says theorem, mathematical facts or theorems. That it says not only x to the power 1 over x, but also all limit of 1 over x to the power r for r positive, any number positive, 1 over x to the power 2, 1 over x to the power 1 over 3, something. These guys are going to be 0. And the limit of x goes to negative infinity of 1 over x to the power r is also 0 for r positive. Note that here, since we are putting negative numbers there, for example, if r is 1 over 2, then we will have 1 over root x. Here, I cannot plug in negative values, so this won't work there. So just consider values of r for which 1 over x to the power r is defined for negative x's. So as soon as it is defined, then you can see this one. So 1 over x to the power r, 1 over x to the power r as this goes plus infinity or minus infinity. Okay, and the other fact which we already discussed when we were learning the exponential functions, it is limit of b to the power x as x goes to negative infinity. Well, let me just plus infinity. If b is between 1 and 0, this guy is equal to 0. And why is that? So remember the graph of these guys. The graph of these guys as b is negative number will look like this. Sorry, b is less than 1 and bigger than 0. It will go to 0. And also, limit of b to the power x as x goes to negative infinity is 0 for b bigger than 1. And for these functions, again, you have the graph. You can keep the graph in mind that the function is something like this. As we go to negative infinity, we have that property. So these two facts are the facts that you have to know. This is bare minimum thing to know about the infinity limits. So we have them in the box. And this guy, fact 2, in the box. Okay? Well, we will learn more about how to compute more limits of functions. But here, let me just write another thing that you see when limit of a function at plus infinity or negative infinity exists, the function as x grows gets closer and closer, maybe becomes the line itself at some examples. And that line has a name. It's called horizontal line. So horizontal asymptote. A horizontal line y equal to L is a horizontal asymptote of f if one of these happens, either limit of function as x goes to plus infinity is equal to L, or limit of function as x goes to negative infinity is equal to L. So either that or that. Any of these happens, then we say y equal to L is a horizontal asymptote for the function. For example, so the examples that we had above, so y equal to 2 is a horizontal asymptote of the function f of x equals to 2. This is the best thing that can happen. It's actually the line itself. Well, how about the second example? The second one, it was 1 over x, yes? So for 1 over x, we have limit of positive infinity and negative infinity of 1 over x. Both of them are 0. So y equal to 0 is a horizontal asymptote for f of x equals to 1 over x. Actually 1 over r for any r positive. Okay? And the other line was y equal to 0 again is a horizontal asymptote for function e to the power x. Remember, because limit of e to the power x as x goes to negative infinity is equal to 0. And the last example was interesting one, that tan inverse, the function tan inverse, it has actually two horizontal asymptotes. One is y equal to plus pi over 2 and y equals to negative pi over 2 are two horizontal asymptotes of function tan inverse. Well, actually, you see that, let me as a final remark, that a function at most can have two horizontal asymptotes. So a function at most can have two horizontal asymptotes. One, when you find limit of the function as x goes to plus infinity, let's say that's L1, and then limit of f of x equals to L2 as x goes to negative infinity, then you pick two different numbers. That's the most possible thing that can happen. We don't have any function with three horizontal asymptotes. Maximum is 2. For example, tan inverse is one of those functions. And you always find the limit at plus infinity, minus infinity. If these are numbers, take those numbers and put as the limit, as y equal to L as the horizontal asymptote, and then check negative infinity. If it is another number, then that's another horizontal asymptote. Okay, so this was an introduction for limit at infinity. So we had the definition, we saw how does that work in terms of the graphs, and these two facts, these are the facts that we will use later in other videos, and the definition of the horizontal asymptote also is given here.